a little bigger. Let's go to stats. All right, so we've talked about how to tidy it up, how to do things in it. Let's talk about how to run maybe some models, statistics, some tests on the data set. So here, we're going to cover how to perform a variety of basic stats, operations, correlations, t-tests, rank sum tests, linear regression, logistic regression, proportion tests. That includes like chi-square tests, which is exact tests. We're going to be glossing over kind of this is how you do it, not necessarily why you do it, when you do it. That's kind of more for a stats class. But if you want to know how to do it in R, this is the way you can do it. So I will say right now, almost everything we've shown you can be done using like tidy and piping and all that kind of stuff. There is a lot of work ongoing to make all these a lot more tidy, but for right now, a lot of the stuff we're going to show you how to do, you need the $sign and things like that, and we'll be using some base R. So first off, correlation. So the core function, COR. Right, so it takes in either one whole big matrix or whole data frame of data, or you put in two things and it'll do the correlation between them. So if these are two different data sets, it'll do the correlation of the columns, but generally you put in one column of the data set, another column of the data set to just one correlation value. So for example, if we read in the Charm City Circulator data again, using read CSV, we're doing the correlation between the orange average and the purple average. Now, unlike a lot of the other R functions, right? That we talked about mean, standard deviation, things like that, variance. There's like an NA.RM argument. This is specified a little bit different because there are many different ways that you can calculate a correlation. So either use the complete observations. That's what we've done here. So the correlation between the orange average and the purple average for when both of these are not missing, it's 0.919. Okay? So there are other options in there. The default is pairwise complete observations. In this case, because we only have two vectors we're making a correlation of, that's the exact same thing here. But let's say you put in an entire matrix of data. Or sorry, not matrix, entire data set. So 5 columns or something like that. If you use complete observations, that will give you the correlations back, but only when every single row doesn't have any missing values at all. So if one of those columns has a missing value, it's thrown out from all the calculations, even though columns 2 and 3 might have a value in that row. So there are just different options for that, and by default, it does a Pearson moment correlation. There's an option to do a spearmint. So in the tidyverse, there is a nice way to actually do this. The package is called CoreR. If you might not have that one installed, so you might have to install it. So again, go to the drop-down menu and say install.packages. It's CORRR. So 3 R's. So for CoreR. Okay, so if we load that up, the way we specify it is we take a data set, we select the columns we want to do correlations of. Okay, so in this case, again, we're just doing 2. So the orange average, the purple average, and then we can pipe that into this correlate function. So before, on the last slide, it just gives you one value. But if we gave it a whole bunch of columns, it will give us back a matrix. Now again, we touched on matrices very, very briefly here. But they're like data frames and tables and that, and they have rows and columns, but they don't work with the pipe and a lot of the plier functions. That's why this is really great, because although we only really care about one value, it still allows you to work on like a tibble or a data frame, so all the filtering, mutate things that you have learned will still work. Now it's a little bit redundant for maybe 2 columns, but this is the output. It becomes a lot more useful when we talk about more columns. So let's do something where we grab a new data, creating a copy of the data set, where it's the circulator data, but we're grabbing any column that ends with the word average. Okay? So now it's orange average, purple average, green average, banner average. So we're grabbing just those columns from this data set. So now we have 4 columns, and now we're going to actually assign the output of this correlate function to COBJ. So this correlation object. That's just what I felt like calling it. So averages, this new data set, just with these variables, we say pipe that into correlate, and here we're going to use complete observations. Okay? So again, there are options for pairwise complete. So for example, pairwise complete, it would look at, in this cell, green average and purple average. It says, in these two columns, find all the cases where it's not NA in both of them and calculate a correlation. That would be pairwise complete observations. In this case here, we said use complete observations. So it said, look at this data set. For those 4 columns, if there's an NA in any of them, get rid of them. So the correlations here all have the same sample size. Okay? If you do pairwise, they can have different sample sizes for the different correlations. Does that make sense? Okay. So I said on the diagonal. So before, by default, it just puts NA on the diagonal. Here, I wanted 1s on the diagonal because the correlation between anything in itself is just 1. And now it would give us a 4x4 tibble, right? So it says this is the row name, this is the column for the correlation. So this is the correlation of the purple average and the orange average. This is a symmetric thing. So these numbers, if you flipped it on its diagonal, are going to be equal. It's like a correlation matrix. It's symmetric. So, for example, purple average and banner average have a correlation of 0.521. Now, this last function I piped into from the core R package is called fashion. So that just makes it a little bit prettier, right? So before, it might show you 3 values, but they really, in the background, this has like 15 digits or something like that. The fashion command rounds it to however many decimals you want it to be. Okay, because sometimes you want to actually present this as a table, and you don't want to have 10 or 15 digits in there, so it actually rounds it down for you. Okay, so the main function we talked about today is correlate for correlation. Okay, and fashion just makes it prettier, and there's other ones to help. Yeah. Diagonal one? Yeah. So if you don't specify that, by default, correlate's like, hey, you don't want me to calculate or put anything in the diagonals for anything with itself. Right? So orange average, purple average. It just says put that as missing. Right? That might be useful because later you might want to filter where the correlation is greater than 0.8 or something like that. Right? And you want it to actually drop those rows because it's not really relevant to find what columns are correlated with orange average over 0.8, and it's like, well, itself is definitely going to be greater than 0.8, but sometimes you want it like this because maybe you want to filter it later, but sometimes, if you're doing a presentation or you're actually, you want to do a plot of it where you actually see on the diagonal everything is 1 or something like that, all this is saying is on the diagonal where you correlate something with itself, put the number 1. Exactly, we'll put NAs on the diagonal. Exactly. Okay? So, I saved this core obj thing out because this function rplot, which is also in the correlate package, allows you to do I don't know if it's a good correlation plot, but a correlation plot. So the idea is each cell is mapped to some correlation value. And so, maybe you're looking at, I think we saw it from before, right, 0.8, 0.9, things like that. Maybe not the best. There's a lot of other options to do correlation matrices, correlation plots. So I will say, there is in the core R package, there isn't really a nice correlation testing. So the core.test function is still the one that I would say most people would recommend. That does a test of the correlations. Again, this one's a little different because you have to put in the vectors. Okay? So that means usually you have to use the pull function to grab the vectors out or the $sign to grab the specific columns you want. It only takes in 2 specific things, right? You can't put in necessarily a big matrix in here. It has to be the 2 things you want to correlate, and it does a test. So again, we're going to use complete observations in this. So this object CT is, when I was saying R objects can be anything. They don't just have to be data sets. They don't just have to be vectors. They can be a whole slew of things. CT is an example of that. CT is, in this case, the output from Ttest is essentially a list, which again, Andrew touched on is a very flexible thing, but more or less, it's something that doesn't necessarily fit in maybe a nice rectangular data set. So let's read the output here. So it's a Pearson moment correlation. You could also have done Spearman, right? Depending on the correlation you want to do. So data, this is the data that went in there. This is the t-statistic, degrees of freedom. This is the p-value. I will say, very sternly as a statistician, p-values cannot be zero. Okay? By the definition of what a p-value is, repeated sampling, finding something as extreme or more extreme, you found something that extreme. So to find something more extreme, it can't have a zero probability. Okay? So usually you give it to some threshold like 0.0001. In this case, the p-value is so low that this is 2.2 times 10 to the negative 16. That is because that essentially runs into the number of decimals on your computer that it can store. Okay, it's a really small number, but a little side rant about p-values. So then it gives you the confidence interval for the correlation, and it gives you the estimate. So this should be equal because we use the same, these complete observations. This should be exactly the same output as core. Okay? Now, if you look at this thing, so we can look at the names of this list. So what are these things named as? So we can see there is an element called statistic, parameter, p-value, estimate, null value, alternative, method, data name, confident. And we could extract these things using the $sign like we would in a data frame, but this is, again, not a data frame or a tibble. So we say CT $sign statistic, and we get these values of a t-statistic of 73, a p-value. It says 0, but again, that's not the case. Now, we show you this because if you do certain testing in R, it might not give you an object that makes sense to you, right? A data frame or tibble, which is what we pretty much trained you to do. So there is a helpful function called tidy in the Broom package. So I know so we've talked about a lot of different packages here, and it's hard sometimes to keep in your head what functions is from what package. So again, we recommend loading up the tidyverse first. Broom, I don't believe is in that, which is kind of a shame. But there is a package called tidyr in the tidyverse, but that's not where the tidy function is. It's in the Broom package. So the creator of it said, if the tidyr package had existed before I made Broom, I would have named it that, but he asked his brother, what do you do? I'm trying to tidy up a data set, what should I call the package? He's like, well, you use a Broom to tidy up, and that's the package name. So the way you use it is you take a testing object, or in a second we're going to talk about models or something like that, and you say tidy on it. And what that will do, although it's not the best tibble or the most informative, it turns whatever test or model you have into a tibble, into a data frame. Okay? So now this object, tidy_CT, has all the things that are relevant that you would want to extract. The estimate, which is the correlation, the statistics for the p-value, the parameter, which is the degrees of freedom in this case, the lower and higher limits of the confidence interval. What is the method? Saying it's Pearson's and giving it the alternative and all the other information into a format that now you can do whatever you want with this, like mutate or arrange or probably filter or really select certain columns from this thing.
Did you say p-value is 0?
P-value, so that is saying it's really, really, really small. I'm saying when you report in your papers, do not put 0.
Is that just the package, repackaging it?
Well, that's just because the number is so small that it's not going to put 16 zeros or something like that. Well, so it's hard because the true estimated p-value is so small. It's smaller than the digits that it's less than 16 zeros followed by some numbers. But again, I'm just saying you might get a statistician on your papers or your reports who's kind of stickler, and I would hammer you for that. Let's just say. So Andrew will be talking more about ggplot 2, but we've talked about Qplot. things like that. So here we're just doing, don't look up here yet, so we're saying Qplot, we're putting in the data set, we're saying on the x-axis we have the orange average, y we have the purple average, these are the two things we're correlating. Here we're just pasting together the correlation with the estimate. We could have grabbed that from CT-tidy, right, which is just 0.92 or 0.919. We're creating just a vector called txt, and we're annotating the data set using the annotate function. Pretty much this will make a lot more sense when we talk about visualization, but we added in here because a lot of people have asked, I want to do a plot and I want to add the correlation to the plot, the estimated correlation. So, and then later Andrew will show you how to add a line, like a linear regression line, all that fun stuff. Okay, correlations, over. T-tests. Function is t.test. All right, it can be specified in a lot of different ways, but for example, here we're putting in two separate vectors, right? T-tests are a test of two different things. It's either a paired t-test or a test of two different populations. By default, when you give it two vectors, or when you give it anything, it assumes the two-sample t-test. Okay, there's an option in there called paired, which I'll show you in a minute to do a paired t-test. So again, we're assigning the output to this t.test, to this object. We're going to call it tt. And we see a very similar output to what we saw with correlation, the correlation test. So in this case, we're doing a Wells two-sample t-test. Here's the t statistic, the degrees of freedom, the p-value is small again. It gives you the mean of x and the mean of y. X is the first thing that goes in there. So for example, on average, the orange line has an average of 3,000 riders over the course of all the data we have, and the purple average has an average of around 4,000 riders. Okay? Gives us a confidence interval for the difference in the mean, right? Taking mean of x minus mean of y, that's what we're getting here. We'll show you this before tidying it up. So in this case, these data points are actually paired, right? They're all on the same day, right? They're lined up where we have a column for the purple, column for the orange, and we actually want to do a paired t-test to see if there is a difference between these two. And you see, you get a different output. Before we had a Welch two-sample t-test. Here is a paired t-test. You could have also done the difference between these two and just did a one-sample t-test on that. But the paired argument is what we're illustrating here to show you that you can do paired t-tests in this fashion. All right, pretty much more or less the output's exactly the same, except the estimates are different because it's a different statistic. So again, I'm just showing you, these are all the names of this listing. It's very similar to the core.test, but again, you can use the tidy function to tidy it up into a table, which might make a bit more sense and gives you kind of all the statistics in many respects that you want. In this case, this is the one sample t-test that we did. So this is the estimate, the difference in means, estimate 1 for the mean of population 1, mean of population 2, statistic, so on and so forth. Okay? So the tidy function is your friend. It doesn't seem that useful just yet, but then sometime you might want to bind. So there's a function called bind underscore rows, where you can bind things together by row. So let's say you did like 5 to 10 different t-tests and you want to bind them together in like a table. This is one way you can do it. Then actually putting this into a table makes more sense. But even then, we wanted to put something in a framework where like now you can do all the functions we talked about, mutate and all that kind of stuff. It'll make a lot more sense when we get to models, because instead of estimate, it'll be like the beta estimate, the confidence interval, the statistic, all that kind of stuff.
It's just a regular table. You can mutate like a title column if you did like 10 of them, and then put them all together so you have like titles for each one.
Yep, absolutely. So here, we're introducing this not just to make things a little bit more confusing, because we want to introduce formula syntax, because it's going to make more sense when we talk about models. So I said before, you can do t.test and you pass in vector 1 and vector 2. That's one way to specify the t-test. Okay? A second way you specify the t-test is a y variable is a function of an x variable. So that tilde, so it's y tilde x. That's the format. And that's what it's going to be for linear models and things like that. So y tilde x, that is what we'll describe as formula syntax. So y, the average, is a function of the line. Now, when you're doing t-tests, right, line can be binary, or it can be a factor or a character, but it can only have two levels. Okay? T-test is only two things. Okay? So all we're doing up here is reshaping the data in a different way so that it's more amenable to this, right? Before, when we had circ, we had a column for purple average, a column for orange average, right? If we want to do this where y is a function of x, we have to reshape it so that there's a column of the average ridership and then a column that says which line is this, purple or orange, okay? So that's why we had to reshape the data, because it wasn't in a format where you could actually do y is a function of x, because x was in y was in two separate columns. Okay? But again, we get the same exact estimate, same exact thing that we had done before. Same exact table and the output after the t-test is done. This is important, again, because this is the way we're going to specify models in the next section. So, the Wilcoxon test, the Wilcoxon rank sum test, which is a non-parametric analog to the t-test, the two-sample t-test. So you got the two-sample t-test and the rank sum test. You have the paired t-test and the signed rank test. So Wilcoxon test is just a non-parametric alternative to doing the t-test. If you don't think normality is really good, it works on the ranks of the data rather than the data itself, so it's a little less prone to, perturbations with outliers or really high values, where that can really skew the mean. It doesn't change the ranks really at all. So again, just showing you that the Wilcoxon test can be tidied in the exact same way. And again, there's a paired argument for this if you want to do the signed rank test. Okay, any questions before we move to the lab? So again, we've talked about correlate, T.test, core.test, Wilcox.test, and really the thing to make it all kind of into a typical way is the tidy function from Brew. Okay? So if at any point you run into something where it says I can't find the function tidy, that is most likely because you haven't loaded the package Broom. All right, so let's go to the lab, and we will be floating around answering some questions. Was everyone able to install the core R package if they wanted? Yes? Give some nods.
Start that message at my Gmail. Pop it in my web browser from the Hopkins email and find the email that answered it. It's the worst system. I assume you're not recording.
I am definitely recording. All right. So let's go over the first one because I want to talk about the second one in a second. After that. So okay, let's compute the correlation between 1980, 1990, 2000, and 2010 mortality data. Again, the data set's called MORT. No need to save this as an object, just display the result to the screen. No NAs. So again, for correlate, what you generally should do is select the columns you want, then run correlate. Okay? But the data here are a little bit funky because the column names are just the years. So if you say mort pipe and then say select, right? We could have used some of those select helpers, things like that. Use one of. That might have been an option. We could pass that. But if we just want to specify the years directly, I would use the tab completion because what it does is, let me see, let's say 1990, right? It comes up. This is the nice thing about using the pipe. And if you hit enter there, it puts these little backticks around it because to R, it's telling it, hey, this is a column name. I'm not actually trying to grab like the 1990th column or something like that. So here we're just going to select the rest of them accordingly. And if you have something and you want to put backticks around it, you can highlight it and click the backtick, and that should encapsulate the whole thing in backticks. Similarly with quotes or single quotes. So if you double click on something and highlight it, it's a little bit hard to see. Sorry, given my the shading, but this is actually highlighted, and I click the backticks, and it puts the backticks around it. But that's useful for not just backticks, maybe curly braces or parentheses or something like that. So if you highlight something and then click one of those kind of encapsulators, it'll work for you. Okay, let's just look at this data really quickly. So these are the 4 years of mortality data for all the countries we have in our data set. And if we do correlate, this is what we get. So the NAs are on the diagonal, but I want to show you, so these are the correlations of different things. So this is the correlation matrix of all the mortality data from 1990 and 1980. But if we say use complete.obs, we should get slightly different results. So for example, which one's probably the best to illustrate this? Let's say this one, 888 in 2000 versus 1980 versus 889 up here. They're slightly different. That's because when we said use complete observations, these all looked at every single row that had no missing data and then did the correlation. Okay? Here, this value right here says, do you have data for 1980 and 2000? Sure, calculate it. Here, you had to have data for 1980, 1990, 2000, and 2010 to go into that calculation. Okay? So, let's compute the calculation between Myanmar, China, and United States mortality data. So, it's a bit of a problem here. The data isn't formatted in that way, right? So, if we view the mortality data, we have the country and then a whole bunch of mortality estimates from all the way back from 1760. If we go all the way up, it's not showing all of them. So let's just say column names, mort. You'll see the last 3 columns. So it stops at 2010, then it does projections to 2030, 2050, and 2099. Okay, let's say we just want to keep them in here for right now. But what we need to do is reshape the data. Okay, because the data is not formatted in the way we need it to be so that we can do the calculations on these 2 countries. So, let's take mort. And I'm going to gather the key. So, the key is going to be called the year because that is what the columns are. They are actually years. The value, I'm going to call it mortality. Okay? And I'm going to gather every variable other than country. So let me just show you what that'll look like. I could have done na.rm on this as well to remove those na rows. So let's do that instead of filtering. Or let's just filter. Okay. So again, we're taking all the columns, we're turning them into rows, we're specifying what we want to call the new column outputs, and I want to remove anything that, I want to keep anything that's not missing mortality. Okay. Notice though, notice year. What data type is it? Character. So it just grabbed those column names, didn't do anything special to them. So let's just call this long, for example. So if we want to turn those years, what am I doing? Into numbers, we have to mutate them into as.numeric. We don't have to do this for what we're about to do, yeah, we don't have to do that for this example, but if you want to plot these things later, things like that is probably going to be relevant. All right, so now we only want to keep three countries, right? So before, the columns were years, the rows were countries. In this case, we want the rows to be years and the columns to be countries when we do this correlation. Okay? So we could have done nothing. We don't have to do this as.numeric year. We could reshape it just as is, but it's going to make a whole bunch of columns because there are a whole bunch of countries in here. So let's just filter the countries we care about in this question. Okay, so I'm going to copy these. So let's say long. I'm going to say filter. Whoa, get out of here. Filter country percent in percent, because I'm going to give it a list of countries that I want to check against. So in this case, I'm going to say Myanmar, China, and United States. Okay? So now I'm saying keep only the rows for these three countries. Does that make sense? So now, if we look at long, we just have these three countries, and anywhere there's actual mortality data for all for that country for that year. So now, to make them back into columns, what are we going to use? What function? Turn rows into columns. Opposite of gather. Spread. I heard like a s, just like a s going out. Okay, so we'll say spread. I'm going to reassign long. Say spread. The key we want is country, because that's what we want to spread out. What do we actually want to fill in there? The mortality. And now we should see that there are different columns for the three different countries, and each row is the year. They might have missing data in there, but probably not. I don't think in these instances we did. We could filter the data where everything's less than or equal to 2010, but for right now we're just going to do the correlation of those. So let's say long, correlate. And so here is the correlation of the mortality data from those three different countries against each other from around 1800 all the way up to actually 2010, and then the three projections. All right. So, although it'll take time to develop these steps, you've learned every single step that we've showed you, right? It's sometimes maybe not always a clear path how to get there, but with combining a lot of these things in different ways actually is where the power comes from with some of these data manipulation steps. So, okay, Again, when you're doing correlate, things got to be in columns to do the correlation. Does that make sense? Did these steps, although I understand if we just threw you into the deep end right now and said do this, it might take some time, but do these steps make sense in sequence? Okay. All right, let's do number 3 using some testing.
Oh, so we could run. So let's click one.
Yeah, let's just see. Yeah, you can you scroll down so that could swap.
Up or down? This?
Yeah, just leave that up. Yeah. That makes sense. Yeah, it's just because I kept reassigning.
Yeah, but it's the most recent.
All right, let's do a t-test. So is there a difference between the mortality information from 1990 to 2000? So let's try just a regular t-test. So again, in this case, we got to put in two different vectors. If the data is if the data is in columns, two different columns, we have to put the data in as vectors. So we say more $. If we say 1990, you can use backticks or you can use quotes around these special column names. But if they were just like random regular column names where they didn't have spaces, they didn't have $signs, they didn't have hyphens, if they just had like underscore separating, you don't have to use those backticks. And for example, 2000. So this is doing a 2-sample t-test. That's giving us a p-value of 0.03, looking at the mortality for 1990 and 2000. The degrees of freedom is 386.23. T-statistic is 2.14. And again, if we wanted to do a paired test, we see a very different picture. And you probably want to do this because it's for data from the same country for different years. Okay? Wilcoxon Test, exact same specifications, exact same way you do it. Instead of Ttest, say Wilcoxon Test. You don't see as much information about the medians or anything like that, or looking at the ranks. You do get this W statistic, which is what you'd report in a Wilcox rank sum test. And again, if you do the paired option, it'll tell you the assigned rank test. Okay, so again, you see kind of very, very different pictures if you use paired or not. This data is generally paired because it's from the same country. Okay, so again, if the data was a little bit different, so we changed the data, so we reshaped it. So if I ran everything up until the point where I reshaped it to be wide again, and I did this, right? So now we have the mortality as a column where it's repeated measures from the different countries. If I did something like, for example, again, this is if I did something where I did like long or Ttest, and I want to do mortality as a function of country, data equals long, it's going to yell at me, and it's going to say grouping factor must have exactly 2 levels. That's because I have these 3 countries in there. But let's say I said just 2 is long, filter, and let's just say country is in China and the United States. If I did something like that, where I just have 2 measures in this x variable, then it'll actually do the test for me, where these are actually tests of 2 different populations. So y is a function of x, but the data has to be in a different format for that kind of specification. Okay, so you can almost get away from the $sign altogether if that doesn't make sense, but sometimes in the testing framework you have to do it. So lastly, I will talk about, or I'll show you something. So we talked about the different types of documentation in R, right? There's the functions themselves, the help files, which you can access using the question mark or just help, correlate. I'll bring up the help file. Sometimes, like I said before, some of these are intuitive, some of them are very much not. So if you say browse vignettes, so vignettes are long form documentation. They're kind of like tutorials. Not every package has them, but a lot of them do, and that's really a lot of times the way you actually see how the packages run. So instead of putting the function itself, you put in the package name, and it should come up with something like this. So these are the vignettes in the core R package. This one's about databases, but if you click the using core R, you should see something like this. This is the package author, or whoever wrote this vignette. So this is showing you how to run correlate. Why do we do it this way? Selecting different columns. Things like focus, where you can look at a subset of the correlation matrix. Other functions to do plotting. Things like that. Okay, so the browse vignettes function if this package has a vignette, and usually if it's a good package, it does, it will maybe show you some more information on how to actually use the package other than just the help files. Okay, we talked about T-tests. So the next extension generally is linear regression. Okay? Now, I will say, if you've never seen linear regression and you've taken this course, I don't know, it might be just like, everything might have been kind of way too much, I don't know. But we're going to be talking about linear regression, which is essentially, you have a y variable, that's continuous. In the simplest form, in simple linear regression, you say that is a function of an intercept alpha plus some covariate times the slope beta plus epsilon I, which is some random noise, right? So standard linear regression, simple linear regression, one variable. The way you do that in R, again, we talked about y is a function of x. So y is your outcome, this continuous variable. X is your predictors. So in this case, we only have one predictor. And we'll show you how to do multiple linear regression. So in this case, we have that data from the circulator. So we're saying fit equals LM. LM is the function for linear model. Okay? You specify it with a formula. Y, in this case, the average ridership is a function of X, which is in this case the line, whether it's purple or orange. And then you specify the data set that the data is coming from. Okay? You say fit, and you get this underwhelming result. In the sense, like, it doesn't show you much, shows you just the coefficients and what you actually did. Okay? So the coefficients, this is alpha, right? 3,033 is the average ridership. But in this case, the reference category is the orange line, right? So this is actually, in this specific instance, this is the average ridership from the orange line. If we actually go back to the T-test, we see here, when we did the T-test, that is indeed the average ridership from the orange line, because of the mean of X. And then that beta coefficient here is actually the mean difference between the two. So this beta estimate corresponds to the mean difference between the purple line and the orange line, and that's how we fit our model. Yeah.
Basically the slope, right?
Basically a slope. So it is the rise over run on that correlation plot we showed earlier. So there is. I thought I took this slide out. Maybe I didn't. So the function summary will give you some summary statistics and show you. Go back. Okay, sorry. I had to refresh. So if you don't have these slides, just refresh. So it was bugging a little bit. So refresh if you have the HTML. Make sure you have the updated PDF. Long 3 is just a data set I had where we kept 3 of the lines, not just purple. We kept the orange, purple, and I believe the banner line as well. So, for example, this is what I'm showing you with respect to if you have a character vector or a factor. So, if you have a linear regression, y is a function of x, and x is a factor or categorical variable that has multiple levels. In this case, orange line, purple line, and I believe it's the banner line. Then you'll get multiple coefficients. It'll in the background make indicator functions for each one of them, and then fit a model. So here, although we have one variable, it gives us 3 coefficients, and this is the output and what you see. Okay, because line has 3 levels of this categorical variable. So summary will give you like a kind of a summarization of the data. There's a lot of people who don't love the way this is outputted because one, it shows the estimate, the standard error, the t statistic, the probability. Then it gives you these, I think, terrible stars that tell you significance codes and stuff like that at different thresholds. Gives you the residual standard error. Tells you how many observations were deleted due to missing this. Then it gives you what I think is probably the least important out of all of this, the residuals. So I believe they give you the residuals to show you it's kind of normal-ish. I don't know. I don't know why they ever give anything like that. Pretty much the summary function, even though we talked about it on data sets, gives you a summary of the data. Summary on a linear model gives you the coefficient or the p-values and t-statistics. That is the way a lot of people do it in R, but the tidy function comes in to kind of save us again to make it a lot more tidy. So now we are running tidy not on a t-test or anything like that. We're running tidy on a model, and it'll give us by default the term in a column, so the intercept and the coefficients, the estimates, the standard error, the statistic, the p-value, and they're all in like normal names, right? You can access these things without backticks or anything weird and stuff like that. But it's a little disheartening in some respects because we don't have a confidence interval by default. So there is an argument conf int equals true, and that will give you the, I think it's conf.int. So tidy.lm. Conf.int equals true. Sorry when I compiled these, because I wanted to add this in. It's conf.int equals true, and that will give you a confidence interval in there, and I'll show you in the lab. But just trust me for now, so the argument is not confident, there's a period between them. So here we're gonna, so that's linear models, LM. Okay? LM, you specify in a formula, y is a function of x. The way we'll show you in a minute how to do multiple variables. You literally just add them together. Y is a function of x1 plus x2 plus x3, where x1, x2, x3 are columns of your data set. And then you specify the data that you are passing in. Yes?
Does it give the correlation coefficient?
The R squared?
Yep.
From the summary, it will. I don't know if tidy will do that by default. Because that, it does make sense to grab that, but it'll print it definitely in the output. Sorry, it's getting cut off down here, but if you do the linear model, it will give you the correlation coefficient down there, or the R squared and the adjusted R squared if you grab it out of this object. I will say though, tidy tries to do things in a smart way where, in the sense, right, you want things that for each row kind of make sense. In this model, that R squared is for the overall model, right? So it would either have to repeat that value over and over again, or have it one time and then NAs, but that wouldn't make much sense. So I'm saying maybe the summary object would have some more information that you'd want than just the tidy version. That's a good point. So I'm reading in a different data set simply for the fact that it's a little bit more, that circulator data set doesn't make as much sense for a logistic regression than some of the data we're going to show you. So here, don't have to worry about all this code. All we're reading is a new data set where it has information as to whether a car is a bad buy or not. Right? Is it a lemon? Is it a bad car? Right? So it has like where the auction was, the vehicle year, how old the year is, the make, model, all this kind of information, the date of it, reference ID, all this kind of stuff. All these other pieces of information. We're just going to look at two simple things for right now. So the vehicle, so again, in this case, we could have done a linear model where the vehicle odometer measure is a function of the vehicle age. That's just a standard linear regression. If we wanted to do, is the vehicle odometer a function of more variables? Again, y is a function of x1 plus x2 plus x3. That's all you do to create a multiple linear regression. If you use the star, the asterisk, that'll do interactions. Okay? You can either create a new column that's like something squared, or you can put square like something vehicle age squared, and it should do the linear version and the squared version by default. So again, we're just showing you here, again, just showing you an example of a linear regression is the vehicle odometer. So how many miles is on the vehicle? Is it a function of a bad buy times vehicle age? So before, this model is saying that if it is truly a bad buy, on average, it has 1,300 more miles than if it's not. and every increasing year of the vehicle, adjusting for whether it's a bad buy, corresponds to 2,600 miles. Now this model is a little bit different, right? So it's saying, is it a bad buy? Increases it about 1,300. The vehicle age after adjusting for a bad buy, and this is looking at whether there is an effect of if the odometer, of how many miles is on the car, is different between whether the vehicle is a bad buy or not. Do you drive more on a bad car or a good car? That's what this is testing. Okay, so this is looking at the mile differential. So again, asterisk, the star, whatever, is how you do interactions. So you don't have to say, and you could have done, is bad buy plus vehicle age, is bad buy times vehicle age. It's not going to do something crazy. It's going to give you the exact same model. Okay, so you can either specify it like that. Let me show you what I mean. Let me zoom out a bit. So I'll show you what I mean is that I wouldn't say it's hard to screw it up, but it will do things that you kind of want. So here I'm going to run all the code up until this point. Okay. So what I'm saying is this. If you do this, let's make this a little bigger. It'll give you this model where the intercept and all three coefficients, all three it doesn't do something strange and add another column and things like that where duplicate columns and stuff like that. It understands that it puts in the linear part and the interaction term. And for example, there are ways, sometimes you don't, sometimes you want this, sometimes you don't, where you can actually take out the linear effect but only keep the interaction effect, things like that. So the negative actually removes something from a regression. So the big difference between here, I think you might have to do this. It should remove that. Anyway, you should be fitting stuff with intercepts anyway. All right, stepping back. Linear model LM. Y is a function of x. You want to add things together. You want to literally add them together to add multiple variables to a regression. The star will do the interaction and also the linear terms. Okay? So this is what I was trying to illustrate. You can do this interaction term, but you actually take out the beta coefficient for the mean shift in is a bad buy. Is that a good idea? I don't know, but sometimes you want to fit models without like intercepts and things like that. So you can actually do that, and the way you do that is literally subtraction. So again, if that variable that you put in there is a character, what it's going to do is going to turn that thing into a factor by default, if it's not already a factor. Like I said before, when we do models, when you create something as a factor or a character, it does things in alphanumeric order. If you want things to be in a specific order, make it a factor with the levels already, or the way you want them. Make them with the levels that you want, and then fit the model. You can make it a factor on the fly, but it'll make these like really ugly names for kind of coefficients. But you can do that. So if you wanted to say factor and specify the levels here, you could do that, but I would recommend doing that in your data set before fitting the model. Okay. Generalized linear models. Poisson, logistic, all that kind of stuff. Not much different at all than LM, except the function is GLM for generalized linear models. And there's an additional argument that's relevant called family. So again, y is a function of x. In this case, we're fitting a model to whether a car is a bad buy or not. What factors relate to that? Okay, is it a lemon? So we're fitting that as a function of the odometer, how many miles is on it, and the age of the car. Again, we're specifying which data set we're using. And then we say family equals binomial. This is doing a logistic regression. So again, these estimates out of the gate are going to be beta coefficients. So in this case, log odds or log odds ratios. So before, this is our logistic regression. We called it GLM fit. And then we did tidy on that. We say conf.int equals true. And this gives us the intercept, the log odds or the log odds ratio, the standard error statistic, p-value, confidence interval, low and high, limits of that. And then there is an additional argument for generalized linear models. You can say exponentiate equals true. This does things in the smart way, right? And what I mean by that is these are now odds or odds ratios. The standard errors, if you actually see, do not change because it didn't exponentiate the standard errors, because in generalized linear models, when you create confidence intervals, you generally make confidence intervals on the beta coefficients and then exponentiate the whole thing, not the other way around. So these limits are now the limits for the odds or the odds ratios. The p-value hasn't changed the same, and the statistic hasn't changed the same. But if you accidentally exponentiated the entire data frame, like you don't want that exponentiated, you don't want that exponentiated, you definitely don't want that one exponentiated. So this exponentiates the things that should be exponentiated and not otherwise. It's a lot of time saying the word exponentiated. So, does that make sense? So generalized linear model, okay? Everything's the same except for what type of family we put in there. And what we do with the tidying. So if you want to grab the coefficients, just the coefficients as a vector from a fit, you can say coef, which stands for coefficients. We're grabbing just the coefficients, and then we exponentiated them ourselves, just to make ourselves feel better, to make sure that what we did before is truly equal to what we did, or what tidy did. So you see 1.307 for the vehicle age, and it's the same, just a little bit rounded off in tidy. So, really briefly, let's look up family. So here are the ways you can specify different families. Binomial, by default, has a logit link, so you can change the link function to probe it if you want to do probe it regression, things like that. Quasi-binomial, quasi-Poisson with a log link, right? So all the different types of generalized linear models that you kind of want to do here. Okay, if you want like over dispersion or whatever with the quasi options. Okay, so the way you would change these from a logistic regression to a Poisson regression is you would simply change the family. Okay, and then you can keep the same family but change the different link function, but that's a totally different model. But sometimes that's what you want to do for like log linear binomial models and stuff like that. Okay. That's modeling it in a nutshell. There are obviously diagnostic tests that you have to do. So if you plot an LM object, it'll do some of the QQ plots, residual plots, things like that. Generalized linear models is a little bit different, but that is more or less how you fit models in R in a nutshell. So, chi-square tests or tests of frequency tables. So here we're going to table the data, and then we're going to run chi-sq.test, which stands for chi-square test. And you should see that it has a whole bunch of options, whether you want to do a continuity correction, all that kind of stuff. But at its very core, we're going to take in a table. We're going to table bad buy, whether it is an online sale, to try to see is the distribution or is the probability of getting in a bad car the same if you got the car online or not. Right? So this is a 2x2 table. We save the option as tab. So again, there are different options for the NAs. In this case, we don't want the NAs if they existed, because that is a different test. So the output of chi-sq.test on the table is very similar to what we saw with the correlation test, T.test. It shows you it's a Pearson chi-square test with Yates continuity correction, the data set you put in there, what is the chi-square value, what is the degree of freedom, and what is the p-value. So it doesn't look like the bad buys are that different just looking at whether it was online or not. Again, if you look at all the names, it's very similar to those other tests I just described. Ttest, Wilcoxon Test, Test, and you can grab things if you want by the $, but again, run tidy on these and it'll give you a tibble that kind of makes more sense. So there is another function called prop.test. So chi-sq.test will work on tables of almost any size, right? That's not to say that they're always correct, right? If the cell counts, the expected cell counts are less than 5, sorry, they'll be correct, but they might not be appropriate. That's what I meant to say. So if the cell counts, the expected value is less than 5, then a chi-square test might not be that great. You might want to do a Fisher's exact test, which we'll get to in a second. But if you have specifically a 2x2 table, you can run prop.test. So that'll do a test of proportions, give you a little bit more information, but you should note that the p-values are exactly the same, degrees of freedom and the statistics, because a chi-square test for a 2x2 table is the exact same thing as a test of proportions. But when you get to 3x3, 2x3, stuff like that, like a 3x3, this isn't going to work because it doesn't make sense necessarily for some of the proportions, but chi-square.test will. Okay? Now, let's say you have small sample sizes or you don't want to rely on that, chi-square, continuity correction, and all that kind of stuff. Fisher.test, we'll do a Fisher's exact test. You put in a table there as well. In this case, we have a 2x2 table. You can change the alternatives. You can change the amount of, you can simulate the p-value rather than use the hypergeometric distribution, which is how it calculates a p-value. All these kind of things. Do you want a confidence interval? Yes. Do you want to change the confidence interval level? Do you want to test against a different odds ratio? Things like that. So Fisher's test, again, can work on, K by P tables. It doesn't have to be 2x2. But when it is 2x2, it gives you some additional things of odds ratios and confidence intervals and stuff like that. Whereas otherwise, it might just give you a p-value. And we see here that when the sample size is pretty large, p-value with the Fisher's test and the chi-square test is generally pretty close. But when the sample size gets really, really, really big here in those cells, sometimes the Fisher.test doesn't work because it has to do a whole bunch of calculations that are really, really big. So, Fisher.test, chi-sq.test, generally you put in a table there, and again, make sure you know what you're putting in there. If there's rows for NA or not, it's testing a different test, whether if those columns or things are not in there, it's testing whether the distributions are different with respect to the data and the missingness patterns. We've done T.test, Core.test, Wilcox.test. All those can be pretty much tidied up with the tidy function. Models, LM for linear models, GLM for generalized linear models. But remember, there's a family argument that you have to change, and if you tidy all them up, it'll give you a nice coefficient table and sometimes confidence intervals, exponentiated if you want odds ratios or risk ratios and Poisson regression. And that is a lot of the testing that we'll cover. So, lastly, we're going to cover. I'm just going to cover one small thing. Sometimes people want to sample their data, especially if you have really, really, really large data. From dplyr, there are two functions that I think are relevant. Sample_n, which allows you to say, how many do you want to sample? Sample_frac, which will allow you to give a fraction of what percentage of the data you want to sample. Now, I'm doing this over the entire data set. Now, if you wanted to do something where you group the data by case control, like the binary outcome, and you wanted to do 20%, you would do different types of sampling depending on how the data was grouped. So let's say you group the data by patient, and each patient had like 100 records or 1,000 records, and you only wanted to grab 10 from them. You could group the data and sample the data and stuff like that. Sampling is a very useful tactic, especially when your data is way too big. So here's an example, which Andrew will show you the Qplot function in a minute. We're plotting the vehicle cost on the x-axis, the odometer measure, how many miles are on it, what is the data set we're using, and we're adding points. So this is the alternative way. We'll show you in the next lecture how to specify plotting. That's not the Qplot function. All right, so lab part 2, and that is the end of statistics. So before we jump to the lab, any questions? Yes?
What's the difference between correlation test
So a correlation test is two continuous values with, so it's doing a correlation, essentially, like almost, a Pearson is equivalent to a linear model where the value is x, one of the values is x and one of the values is y. That r squared value from the linear model is actually the same. The r squared is actually the correlation squared if it's just two variables. So it's two continuous variables, the correlation between the two. Chi-square.test is done for frequency tables.
And for the linear, when we put plus between variables, does it mean it's multivariate regression?
Yep, multivariable regression, exactly.
And the star is interaction.
The star is interactions. So it'll do the multivariable plus the interaction term between the two. So there is a function. So I updated these slides, but I don't know if it actually came through. There should be a slide on, I don't know. There are two functions that are probably otherwise relevant. So the AOV function does an analysis of variance, but I will say I don't do ANOVAs almost at all. I do linear regressions. The ANOVA function, though, is very useful because what you can do, we'll do ANOVA tables. So if you do, for example, a model with the interaction and a model without the interaction, and you run ANOVA on that, that will test the differences between those two models if they're nested. So what I'm saying is, let's do this. Let's do fit2 is this. Call it fit int. So fit2, fit int. All right, so these are the two models. They're nested. This model is nested inside this one. If I say ANOVA on fit int, this does an analysis of variance test for the two models, giving me the RSS, the sum of squares, and things like that. I could have also done, say, fit int2 is online. Is that the cars is, okay, is online sale. So this is doing testing of the nested models, where this model is nested in this one, which is nested in this one. So it's doing an ANOVA table of those. So it's doing F statistics for those terms. Right now, it's not as relevant in some respects. I mean, I would say the comparison of model 3 and model 1 might be a little bit more relevant because pretty much if you only are adding one variable, you can look at the T statistic. But let's say we were doing something like this. So we're saying, is adding whether it's a bad buy and the interaction with vehicle age plus online sale, is that adding significant improvement or reduction of the residual sum of squares from our model? Okay, so this is testing a group of terms. This is a different hypothesis test. This is testing whether all the beta coefficients for everything that's not in model 1 but is in model 2 are equal to 0. So it's an F test. It's different than just testing each t-test individually. Okay? So again, a lot of this stuff comes out with things that aren't very tidy. The tidy function tidies it up for you, gets it into a data frame that allows you to kind of work with it. So let's jump to the lab. And then Andrew's going to take it away and take us home with some plotting. A lot of plotting. We're more or less going to go over questions 4, 5, and 6. Pretty much questions 7 and 8, you sample the data, and then you run a linear another model on the data just to show that a subsample of the data probably gets you pretty close to the coefficients. So we're only going to go over 4, 5, and 6.
For some reason, we have to try to put it or something. That's like just a question. Yeah, that's it. She could.
motions in the player,
Yeah.
the mouse,
Yeah, it might work.
and then
R still.
getting close.
All right, so let's fit a linear model. Number 4, let's fit a linear regression model with vehicle cost, VHB cost, as the outcome and vehicle age and size as predictors as well as their interaction. Save the model fit in an object called lmfit_cars and display the summary. So, we'll say lmfitCars equals, say lm, and again, first argument is the formula, second argument is the data, so you can either specify them or put them in order. I would recommend putting them in order. VHB cost is a function of vehicle age plus size, and you could say plus vehicle age times size, data equals cars. You could have also just done the interaction. It'll do all 3 coefficients for you, but sometimes this might make more sense. So you're actually saying, like, if you just did this and then you actually look at the model, you're like, I have 3 things out there. Where did that come from? So we see a lot of coefficients were created. Just to be clear, let's say dim cars. Cars is pretty big, 72,000, 73,000 rows. So although this model is very, very big, I wouldn't say it's, it is pretty, I wouldn't say overfit, but it's probably a pretty large model for this type of data. But we are seeing kind of what the interaction between these 2 things are. Again, this data has not been cleaned in any way whatsoever. So you see like vehicle age size null. So for some reason, some of these columns, the size of the vehicle is null. So we should have cleaned that, removed that, changed that before fitting this model. But now we have that, and we can run summary, lmfitCars. Now we have the model output, and we can see all these coefficients, p-values, things like that. Again, we could say tidy, lmfitCars, and we now see we have, in a much tidier data set, the same information more or less. And we can put in confidence intervals, which is not getting viewed here, but I'm just going to pipe that into view so we can actually look at it. We do see confidence intervals low and high from that data set. Now, I'm going to show, because that question was asked about R², so you can assign the summary output to something. If you say sum fit and you say $, we'll put this back up, you should see all the names of this thing, one of them being R², and one of them being adjusted R². Oh. There are other functions, extract AIC from the lmfitCars. So it'll give you IKE information criteria. There are other model selection tools you can do on these types of models. There's a package called Leaps that'll do an efficient model selection criteria, but there's a whole bunch of them out there. I would always say, though, be wary of p-value selection with respect to models, especially if you're not doing any validation. Okay, does that make sense? We could have done the interaction just itself or done the addition. So I will say this. Starting out in R, you're going to make typos. It's going to happen, period. R, so you're learning a new language. So it's very much like you're talking to someone who knows the entire language. They're kind of a little slow. And they're the strictest grammar person you've ever met. So if you took a grammar class back in the day and the teacher was very strict, think of the most strict person you've ever had on grammar. And then also they're kind of dumb. That's R. Okay? So it's not going to guess. It can't guess. It can think only so much as we allow it. Right? So that's the way I would start considering talking to R in many respects. They know the entire language, and they say, you have to specify it my way or the highway, but also I'm not going to make any smart guesses because I'm kind of dumb. That's R. or general computer programming in general. So, create a variable called expensive in the cars data set that indicates if the vehicle cost is over $10,000. Use a chi-square test to assess if there is a relationship between a car being expensive and it being labeled as a quote-unquote bad buy. So I'm going to change the cars data set. I'm going to take the cars data set. I'm creating a new variable. I'm changing the data, so it's going to mutate. And I'm going to say expensive equals VB cost is greater than 10,000. Okay? So, if you really want that to be just 0 or 1, you could say as.numeric on that. You could have done this times 1. But generally, I generally keep that thing as a logical, true or false. So, I'm just going to do that. Let's just select expensive. So we see now vehicle B cost, which trues and falses where you'd expect it to be. Okay, now let's do a table. I'm going to call it tab. Let's do table. Cars, is it expensive? Cars is bad buy. Okay, just creating a two-way table. So let's see what we have. We see, even though if we tried use NA, if there are any, there are no missing values in this data set with respect to the vehicle cost or whether it's a bad buy. And now we can do chi.sq.test tab. It gives us a chi-square test. Could also have done a Fisher test. And almost always they give, especially for large samples, they give almost always the very, very similar inference. Okay? So create new variable, mutate, run a table, pass that table into one of these tests. Okay? So for the logistic regression model, where the outcome is whether it's a bad buy, so the is bad buy column, and the predictors are expensive status, vehicle age, and save the model fit in something called log fit cars and display the summary table. So again, instead of the LM function, we're going to be using GLM. Say is bad buy is a function of vehicle age plus expensive data equals cars. Now, I'll just show you, if I just run this, we see it gives us a model. But by default, in GLM, the family is Gaussian, which means this is a linear model. Right? So in order to make it a logistic regression, we say family equals binomial. Very different model. Right? Different intercept, different coefficients, because it's a totally different specification. Right? I will say, let's say we screwed up and we're trying to do vehicle age, and if it was a bad buy plus expensive, and you try to do something, say it's binomial, let's change that back. But you try it and it says like, hey, what are you doing? You're trying to do a binomial model, it's like, no, vehicle age is all over the board. It's not between 0 and 1. You can technically fit a logistic regression where the values aren't just 0 and 1. They can have values within 0 to 1, but that is kind of a different kind of a modeling behavior. Okay. Yeah.
But I saw like some people they write this type of like link to Sally.
Link is something else?
Yeah, equal. Like that.
You don't have to if you're using a logistic regression. But there are other link functions. Oh, of course I had that. This is a different model. So I said a different link function. So instead of the link being like the log of p divided by 1 minus p, stuff like that, it's just not the logit function. This is the probit function. This is like probit regression where it maps like the normal the inverse link function from the normal distribution. So by default, if you're doing logistic regression, which you're doing 9 times out of 10, you don't have to specify the link. Okay? So now we have log fit cars, and again, these are beta coefficients, which are log odds or log odds ratios. And if we say summary, log fit cars, you'll notice you get some information. You don't have an R-squared value because this is that measure is kind of about deviance and things like that. There's not a one-to-one correlation between R-squared or adjusted R-squared in logistic land. You still see the coefficients, some residuals. You see the dispersion parameter from the binomial family is taken to be 1. If you want to do an over-dispersed or an under-dispersed potential model, you can use the quasi-binomial, right? Just different modeling things, different assumptions. And then you can say tidy log fit cars conf.int equals true exponentiate. I'm just going to copy it. True. So it might take a second because it might be running like a profile likelihood in order to get the confidence intervals. So now we have the estimate standard error, p-value, statistic, low, high, confidence interval, and now these things are odds ratios or odds or odds ratios. No log anymore. Okay? So, really briefly, I'll show you what we were showing. We were just going to go with, in this data set, say 10,000 rows, right? So, dim cars. Cars is 70,000 rows. Let's say maybe cars was like 1 million or 1 billion rows. That might take a little while to run that, so you want to maybe do some different regressions where it was like, hey, we want to just try some things a little bit shorter rather than this. So I'm just going to show you the difference in the coefficients between taking a random sample of 10,000 rows versus the entire data set. So 10,000 rows, that's up here, and this is the full data set. We see pretty similar beta estimates and things like that. So 0.38, 1.33, or sorry, these are odds or odds ratios, right? They're pretty similar. They're not identical, right? But sometimes you can really get a good idea of what's going on in your data set if you just do a small sample or smaller sample, right? Not as big of a difference with 70,000 versus 10,000. They take about the same amount of time. If we're talking like 1 million or 100,000, or especially a complex model, taking a subsample and doing something like that can be beneficial. All right, that's stats in a nutshell. All right, that's my whole field done. It's done. That's all you need to know. But there are packages. One is called LME4, which is for linear mixed effects models. LMER, which is a different one for mixed effects models, which has a function GLMER, Glimmer, which is for generalized linear mixed effects models. So you want to do a random intercept, where you have a logistic regression, things like that. The more complex your data is, you might have to go to those models. But R generally has a pretty good mixed effects modeling framework. But a lot of times, logistic regression, linear regression, tabulations, especially when you're starting out with a data set, those are the things you should be doing, especially to see the relationships. I've done, so Friday clinics at the School of Public Health are for students, especially if they want stats help. It's in the BioStat Consulting Center, and I did that for a few years. And I will say people came in with very, very complex questions. They said, I've repeated measures, logistic regression, and the exposure is binary and stuff like that, and I want to fit this really complex model. And my question would always be initially like, did you do like a 2x2 table? And their answer almost undoubtedly would always be no. And I said, well, let's try that. And you look at the 2x2 table, and the treatment versus the control, the outcomes are almost identical with respect to proportions. And I don't care how fancy your modeling framework is, you're not going to necessarily overcome that. And if you do see a table that's like they're very similar with respect to outcome. And then you do a fancy model and it says something different. You should be more worried about that fancy model. So, it's kind of my plug that a lot of the basic stuff gets you a really long way, and then when you need to go to the complex stuff, R has that at your disposal. Okay? Now let's see how to plot stuff. Andrew gets the fun plotting stuff. Yay! Yes?
What is the